Hey everybody, this is Larry. This is me going over Q4 of the weekly contest 270. Oops. Valid arrangements of pairs. So, hit the like button, hit the subscribe button, join me on Discord, show me some love. This one's really hard. I don't know. Well, I mean, okay. If you don't know how to identify this, is it's going to be very hard. So the thing that I would say is, before I get started, I would say that I don't like this problem, at least for competitive thing, and also interviews, right? Because this is not going to be an interview problem, at least not the complexity that you want. Like I could see this could be an interview problem if n was like maybe 50 or something like that, because maybe we'll talk about it in a bit. But given that you're looking for a linear time solution effectively, this is not going to be an interview, so don't worry about it that much, because it's you have to know a way as we like you have to know a very specific algorithm, an idea, and if you don't, maybe you probably won't get it. I mean, it's not in theory, it's not difficult to implement, but to be honest, looking back, I did not. I haven't had. I don't know if I ever did this problem. And I never, like I know of it, but I didn't need to do it. But I'll give you the resources you need because this is just like a cookie cutter problem of, hey, do you know this algorithm, right? And without further kind of, but anyway, I just want to say that and it doesn't really come up in competitive because this is just literally, do you know this algorithm, right? Like, which is not interesting for most respectable competitive platforms because, it's just not interesting, right? Like, I don't know. I don't consider it. That said, I mean, if you want to have fun, this is a fine problem. This is and I also think that like looking at all the top people, like I don't think that I think most reasonably top people can identify what the algorithm is, or maybe not the algorithm, but what the problem is immediately. Because I certainly did, and I don't even have that much experience I haven't done this in a long time with Euclidean path, and that is the thing you're trying to do. So basically, and this is the thing to Google for, is Euclidean path. The first thing you know is that you're trying to find an Euclidean path, and in this case, it's directed. I actually spent some time because I thought it was undirected for some reason, because I thought you could, swap back and forth. And I did eat a lot of penalties. I got the wrong answer because I didn't realize it was directed, and then I got memory limit exceeded, which we'll go over in a second, because I think there's this one I deserve the time limited. Maybe I deserve, but it's still like a really tough thing to implement. But we'll go over it in a short while. But if you want to know more about how to solve this, I'm just gonna ask you to be honest. Like that, I'm like this is a topic that can go into as much depth as you want. Like it's like how to do sorting, right? Like I mean, I could explain to you sorting, but like there's just so much resources, and also like it's not like it doesn't really make sense, right? So I will tell you how I would explain my implementation, and kind of assume that you do some research before continuing this video. But if you search for this, you'll find something called, what is it? How do I spell it? Sorry. Let me see. What's this? The person's name? It's like Hauser, whatever. Sorry, friends. Oh yeah. So I would look up this for competitive, and so I'm just gonna go over my implementation, and then I'll go over how I got my what happened to these other ones. Like I said, one of them was just I forgot which, because I'm very familiar with undirected Euclidean path, but I haven't done directed Euclidean path in over 10 years, over a decade. I might have done it once, even if I have done it. Like I don't remember it coding wise at all. So I had to Google it. I'm not gonna lie, but like I said, I don't think it'll be on an interview. So you could take it as you will, and maybe I'm wrong. So and then you'll be like, Larry, I just got this weird interview that asked me this. I'll be like, well, sometimes you just get unlucky. Anyway, so yeah, let's go over my solution. So basically here I track the in degrees and out degree. So there are two possible ways to choose the starting node or starting word. Oh, one thing to say is that in this case, the nodes, so this gives you the edge. You can say that this edge is from going to 5 to 1, and then so now the nodes are the numbers themselves. So 5 is a node, 1 is a node, and 5 going to 1 in a directed edge means that there's an edge from node 5 to node 1, right? So then we talk about degrees, and now we just keep track of in degrees and out degrees for each node. And the reason why I did the plus or minus 0 is so that I could have the key later so that it can be 0, right? Otherwise, it just wouldn't exist. So yeah, I keep track of this, and in edges, I put edges as y. And the reason why I have put in a deck is something that I'll go over in a second. Is an action optimization for me. I'll go over the progression as to why I need it. But yeah, the starting node, there are two possible starting node. One is that every node has the same in degree or out degree. You could, in a very simple version, you have two nodes, and then you have, A going to B and B going to A, right? And everything is an outflow of that. So basically you have a cycle, and then in that case, whatever node you start with, you have to enter that node. The second scenario is this one. And also, like in that scenario, you could choose any node. It doesn't really matter. The second scenario is this one where you have the in degree plus 1 is equal to the out degree. And what that means is that you have one node that has one fewer node coming in than going out. That means that you have to go out once and then end at another node, right? So that's basically what this means. And in that case, you have to choose a starting node. I made a mistake here the first time, which maybe we'll go over. It doesn't really matter. But yeah, this is the algorithm. And okay. Let's say we have a starting node. Like I said, if it doesn't matter which starting node, I just pick a random node. So yeah, I just take the first pair, and it doesn't really matter. This is a random node. Otherwise, we start from the starting node, and then here we have the path. And then the idea is, and like I said, I'm not going to go over this explanation too much, to be frank, because like I said, this is just an explanation of this algorithm, which has a lot of proofs and stuff like this. Maybe I'll do a video on it in the future, but I'm losing my voice. But for the purpose of this video and just going over this explanation, but basically, for every node, we just recursively go to that edge. And then the idea is that, in a very rough way, like I said, with the proof and stuff, I'm not going to go over. But for every node you do recursively, you're basically going from A to B or U to V in this case. And then V, you go you do the little path and then you go back. And then at the very end, you expect the node to go back from V to U. And then that's why we append the U, except for that. You're supposed to prepend it in the algorithm, but I wrote it this way so that I can just reverse it later. It's not a big deal, right? And that's pretty much it. Because each edge will get popped off once. This is linear time. So that's, each edge can only be popped off once. There's actually an additional check in the canonical implementation of this algorithm, but there always exists a valid arrangement, so we don't have to do that check. We can just, because that is actually makes the problem a lot harder, but we can assume that there's always a path back, except for to the first node. So we just do this thing. And then at the end, we add this to the path, because now we know that we process all of the stuff, so then we have to go back, right? So that's basically the idea, roughly speaking. It's a little bit hand wavy, I know. And then now at the end, we just reconstruct the path, and because every start n is equal to the next start, so you can just look at adjacent elements on the path and then recreate this thing, and that's pretty much it. Like I said, so this is linear time in the number of edges. This is linear time on the number of nodes, and this is the linear. This is in total linear in the number of edges, because every time you process an edge, you'll get popped off. So it's not possible to process each edge more than once. So it's going to be linear time. That's pretty much all I have. Like I said, if there are any more details, just do some Googling. I apologize for that. So the one thing I would say is, that let's go over my memory limit exceeded. Is this my memory? No, this is not my memory. Let's go over my memory limit exceeded and then time limit exceeded, just for educational purposes. So I got memory exceeded because if I just did for v in edges of u sub v, which I had before, if I had something like, let's paste it here really quick. So let's say I have this. So this is my first version, and you could watch me solve it live next. If I do something like this, I get, oh, this is not supposed to be a deck. So in my initial version, this is a set, right? In my initial version, this is a set. So then, okay, sorry friends. In my initial version, this is a set. And then the set changed size during the iteration, so I cannot remove it because this changes the iterator, right? So that's why I was like, okay. So then my hack to fix this is to convert it to a list. Unfortunately, because I'm creating it to a list, it makes a copy on every recursion. That means two things. One is that it makes it super linear, because now, even if you remove this edge, you're still processing it in the future. So, or even if you remove this edge, within this recursive stack, you're still allocating extra elements. So that's why I got memory limit exceeded. So then the next thing I did was I changed it to a dictionary where I just update this to false. Unfortunately, this gives me time limit exceeded. And the reason why this time limit exceeded is because even though we do this thing, we still go through it becomes effectively, roughly speaking, n squared, where n is the number of edges, because in a way, let's say, let me just write, I mean, I'm not going to copy the rest of it, but let's pretend I have this, right? The reason why this gives me time limited is, for example, let's say edges u of keys is equal to 1, 2, 3, 4, 5, right? This is actually a set, but you know, but the thing is that let's say we go down from 1 to 2, and then let's say 2 has an edge to 5 or something, so then 5 gets removed, or something like that, or let's say 1 goes to 2, goes to 3, to 2, to 5, right? Something like this. In this case, in this instance, we remove the 5, but when you pop back off the stack, once you go back to here, you still check to see if the 5 is here, but this means that this effectively becomes n squared time, because now your core stack looks something like, you know, in the context of 2, let's say this is 2's list, edge list, and 2, you would look, the edges look like this, and then it goes, let's say 3 only has a list to 2, and 2 now has an edge from 1, 4, and 5, and then you remove the 5 here, which you actually want this to not process, but because you do, it just creates duplication of work. So it's no longer true that you do O of 1 for every edge, right? You do, like, it may get to n squared because you may look at each edge n time roughly, right? So that's basically why it became time limit exceeded, which is very unfortunate, but that's what happened. So it took me a little bit of time, and you could kind of see it in, you know, it took me about 3 minutes to come up, and I wasn't sure about this, to be honest, when I submitted it. If you watch me solve it during the video, I actually implemented this really quickly, but I wasn't sure about it. So I actually was doing some other stuff for a couple of minutes before I submitted, which actually ended up, you know, being silly. But But yeah, what I end up doing, which I like as a challenging thing, because like I said, I've never done this before, so it is new to me. So I'm proud of that for that reason, which is that I convert it to a deck because I just go, okay, if I remove if I pop left, and this isn't an iterator anymore, but if I pop left, then that means that even if I go down on the stack and I remove an edge, like once I go back here, this goes to the pop left, right? Because then when you return from previous stack, it just goes through this again, and then if it still has an element, then we go this, right? So that means that now each edge is executing once, and that's basically the idea behind that optimization. I hope this helped. I mean, I actually was very proud that I got this, to be honest. I mean, I could have done it faster or whatever, but yeah. That's all I have for this one. Like I said, I didn't really go over the algorithm that much. But yeah, these are the two things I would recommend Googling. And I just want to give you a snapshot of my code. This is the first half, and this is the second half, maybe. But yeah, that's all I have for the video. At least in terms of explanation, you could watch me solve it live during the contest next. I actually knew how to solve this immediately, which made this a silly problem, but it still took me 27 minutes and 3 wrong answers to get it. So you can. Anyway, yeah, I'll see you in a bit. You can watch me solve it live next. Okay, good. That was a yikes, but let's go. Focus. Say what? Pairs of eyes started and if every eye we have ends of eyes equal to starts of eye. What does that mean? So it isn't put pairs. Oh, just like this is the Euclidean. This is annoying. Two pairs are exactly the same. I had to look this up. I mean, this is Euclidean path. Is it easy right now? I mean, I don't think so. But this is awkward, right? Because you can. This is an annoying problem to solve, or like just not really interesting either. Just point it out just to make sure. I have to look this up. I don't remember that. I mean, I know the idea about this algorithm, but I don't. Yeah, it's just Euclidean path. So, I mean, there's a couple of different implementation. I have it somewhere as well, but it's just silly for me to. This is going to be y square, which is probably too slow. I have this implemented somewhere. This is such a silly problem. This would never be on an interview. And even then, like, what's the point? Because basically you just keep on finding cycles things. This is like if you haven't implemented or not, and people haven't done it yet, because this is just, it never comes up. Oh, that's not true, maybe, but I have this implemented somewhere, but I can't find my code. Or at least maybe that's not true, but I don't have a linear time one. So I'm just Googling it. Basically, you just find cycles and then you kind of go into it. Oh yeah, if they're odd, we want to do something. Oh, there. I might not know how to do it, to be honest, but this is such a silly, stupid problem. It's just like, hey, do you know this thing? And to be honest, I don't know that I do. I guess. I mean, I know enough to know to look for it, but and the code is probably not that bad. But I just don't have it ready. Let's create a adjacency list actually. Set. That's not true. Yeah, actually, I guess that's true because there's no two pairs. I don't know if that makes it easier or not. I mean, wouldn't make it harder, but I don't know. I'm surprised no one solved it yet because I imagine, okay, someone solved it now. I imagine the top people have it. I don't have this implementation. I think I had one that's n square, but it's not. This n can be pretty big. Yeah, people got this, but apparently I have written an article about this in the past. That means that we can choose anything, so just choose doesn't really matter. Yes, that's unfortunate actually. I guess that references that. I forget how to do it. How do I do this in a good way? No, you wanted to update this though. That's the point. No, I think that's fine. Actually. I don't even know when this is happening. I don't know if this is right either. It's right for these. I don't know if this is gonna time out. Like, I don't know why I need this. Oh, I see. Because it may get deleted in the future in the stack. Okay. I mean, I'm not going to solve this that quickly anyway, so let's Does it have to be in this order? Huh. Oh, it's directed actually. Okay, so I'm wrong here. Yeah, I actually misread this one. X has to go to Y. Yeah, then this doesn't happen. That's not good. Oh, because I don't start correctly anymore, maybe. Because now this is directed. What we want is an odd number of out degrees. Where do we start again? We start the only one, there should only be one where there's no in degree, right? So, okay. Nope. I misread this one a little bit. If in degree otherwise, then it doesn't really matter which one you start. That's not true. It has to be, well, if there cannot be multiple with this, and there has to be at least one with this. I think we're okay here. Degree not found. I think we don't have to care about n. Actually, we don't use it anyway. Well, that's not the answer. Also, this is not even the input. Did I mess up the in degree? Out degree? In degree of y degree. Oh, because this only looks at the keys. So what we actually want is okay. Edges are wrong. Why are my edges wrong? Why am I doing things backwards? Oh, because I'm constructing my path backwards. So actually what we want is looking at it backwards. Okay, so now I think we're right, but are we? I don't know if this may time limit exceeded, but that's fine. As long as we don't get a wrong answer, then we can think about optimization maybe. I think this may time limit exceeded anyway. Which is unfortunate because it looks like it's going to be time limit exceeded. Oh, okay, huh. That I did not expect. It may be this thing though. Let's see. Because that part I wasn't sure about, to be honest. So let's see. Okay, so they're both none. Because maybe it's not true that we can start from any spot. I actually don't remember that variation of it. That variation of directed Eulerian path. Okay, so that means that they're none with the in degree of 0. So then we should be able to start from anywhere, right? Let me just look it up. Path directed. Okay. I see. Okay, so you do need out degree. I actually don't know this one. I mean, I know how to look it up. I just didn't. Maybe I should have. But so this is if in degree is equal to out degree plus 1, is it, or the other way? Yeah, no, this is right. Okay, let's see again. Okay, so this is good except for this one. It's either that or all of them are in degree, and then in that case now it really doesn't matter. And then now I'm printing out from 489. What is the expected answer? The expected answer is still different though. That's unfortunate. Maybe they're multiple? No, that doesn't make sense, right? There should only be one case. Did I get this wrong? Well, my answer for the first one's wrong, so that, and I put 1 instead of, why? Oh, wait, no, out degree of 5 is 1, so out degree plus 1. Oh, I've mixed it up. I think this should be this. Whoops. 156. This is the same as this, right? Okay. And the other ones match. Yep. Okay. So let's remove some print statements. Maybe this one's, I don't know. We're very close to time limit exceeded, so let's not do that. Okay. Okay. Let's just print this. Okay, well that's unfortunate that this does not match that. Oh, it could be multiple answers actually, so because it may be cycles in the middle, so that's fine. And the last one's 489. Let's double check. Yep, the last one's 489. I think we're okay with that. So just want to double check. Still may get time limit exceeded, but let's give it a spin. Would suck to get time limit exceeded, but because I don't know what I would do. But we have like an hour, so maybe we could figure it out. This is such a silly problem though. It's a waste of, oh, memory limited. Huh. It's because we're creating lists here. How do I do this in a good way? I actually don't, without changing the list in a good way, because basically just recursion is taking too much space because we're creating a list every time, so it becomes non-linear. So that's why it's memory limited. How do we modify the list in a good way? What's it called? Without doing this, right? Did I click? I thought I clicked. How did I get around this? I don't know how to get around this, to be honest. How do I, without change? So I'm trying to do this without changing the set as well, which is not great. Yikes. I mean, I guess the way to do it is actually what do you want to do it? For everything we add a hash table, I guess so. True, right? If edges of u of v is true, then we do Wish there was they gave us the test case though. So it made one okay, that ran at least. Nothing changed, so okay. I mean, this is more of a YOLO, to be frank. And the server seems to have issues because I don't know if I submitted or not. And even just refreshing is giving me timing. I don't know if it's my computer or not though. Oh, there is the pending. I had a really good time on the first 3, it seems like, but the last problem is giving me fits, and I already have 10 minutes of penalty. So that's not going to be just, oh, time limit exceeded is a little bit rough. I wish they gave us like one thing for it, because I don't know how to do it. And it may be that this is too slow, to be honest. But we only look at each edge once, so it should be okay. Maybe. I don't know. Is this any faster? I mean, we're just looking 2 lookup tables. I don't even think I can go that much faster without changing this algorithm. But this only this is slower even, right? I don't know if I know how to solve this one in fast time. I mean, this is a silly problem. It's either that or I need to change the language, to be honest. Maybe it's a Python thing. If this is a Python thing, I'll be really sad. Okay, let's what should I do? Let's give this a submit, and then oh, it accepted. This is a weird thing though. I don't know. And also I have like, was it 3 penalties? So that's I mean, but this is such a stupid problem, to be honest. And I don't mean that. I mean, I try to be as respectful as I mean. I just mean that this is just a token problem. There's no way this is going to be an interview question. It's not even an interesting competitive problem. It's just about, you know, and you saw that I did like 3 ways of optimizing it. I don't know. I mean, I don't know. I feel like I should have gotten an earlier time on that one, just because so much of that is on penalties. And like I had a really good top first 3, right? I guess relatively. I don't know where I was, but it seems like I did pretty okay. And to be fair, 2 things, right? One is I think I got this one immediately, like in concept. But I would also say that all the top people got it in very quickly. I don't think anyone had issues with the idea, but it is like the implementation that's a little bit weird. And even like very good people have multiple, well, you know, a good amount. So it's like a little bit luck. I don't know how much of it is you know, Python versus whatever, but I don't know. I just feel like that's a really silly one. Like even though I got accepted, I wasn't sure that I got accepted. So yeah. Like when I submitted, I wasn't confident about it, right? I mean, and also like it looks exactly, I wouldn't say exactly the same, but it's not that different from all the other ones. I think like we're just talking about some constants here. Like the time limit, maybe the memory limit exceeded. Maybe this one's my fault. This one I was just wrong. The memory limit maybe is my fault, but this time limit I'm not happy about. Oops, that wouldn't show you anyway. And also the server's having some issues, so I don't know. Like changing from here to what I had is not an interesting change, right? Like this is such a micro optimization. Maybe not. Maybe I'm missing some nuance with the complexity analysis, because this can degenerate. Because yeah, I don't think that's wrong in that. I think this can degenerate into like an n squared type thing if you're not careful, and maybe I'm not careful here. Where that this actually makes it so that, because the guarantee for linear time, the guarantee you want is to make sure that each edge gets visited once, and this doesn't do that because you get to visit it more than once, but in doing the check, because it doesn't get removed. I don't know. It's such a weird problem, and I don't have experience in this one. So I mean, this is gonna fall just because I have so many penalty. We still have like 10 minutes of penalty or something. So yeah. So let's yeah. Thanks for watching. Hit the like button. Hit the subscribe button. Join me on Discord. Thanks for your support. But yeah, come to Discord if y'all want to chat about these problems in a more interactive way. I'm actually been becoming a big fan of Discord, so come, man. Yeah, there are a lot of smart people there now. But yeah, stay good, stay healthy, keep grinding. It's tough, I know. Keep going. I believe in you. But yeah, stay healthy. What else did I say? To good mental health. I'll see you later and take care. Bye bye.